Okay, so let's look at this example here. It says we're going to look at the set of all solutions of the homogeneous linear system in n variables is a vector space under the operations inherited from Rn. Okay, so we're talking about vectors that are solutions to the homogeneous linear system in n variables. Okay, so if we take a typical equation from that system, let's say C1 x1 plus dot 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 plus C sub n x sub n equals 0. Well, and we take a, let's take two vectors that are, that satisfy these equations. So let's take V equals V1 all to Vn, and we'll take vector W, which is W1 all to Vn. Let's say these two vectors satisfy the equation. Then their sum would also satisfy the equation, right? So how would we write that? Well, let's write it out. So if their sum, so if these two satisfy it, then their sum should satisfy it. So how do we write that? Well, let's write it out. So it would be written out like this. C1 V1 plus W1 plus C2 times V2 plus W2 plus dot 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 plus C sub n Vn plus Wn. Right? Well, that's going to equal what? We can distribute. So that's going to be C1 V1 plus C1 plus W1 plus C2 V2 plus C2 W2 and all the way to Cn Vn plus Cn Wn, right? Well, now we can use the commutative property and move things around. And so we're going to get what? We're going to get C1 V1 plus C2 V2 plus dot 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 plus Cn Vn, right? So we can group that together, plus C1 W1 plus C2 W2 plus dot 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 all the way to Cn Wn. And of course, because we know that these two vectors satisfy the equations, we get 0 plus 0, which equals 0. And all the rest of the conditions follow similarly and are just as routine. Now, we did omit the symbol for multiplication. So when we're multiplying two real numbers together, we know how to write those. And when we write a scalar multiplication, we write that using symbols, right? But really it's about context. So a lot of times we drop the dot like in this case here, because we know from the context we're just multiplying two real numbers. Okay? If we're doing scalar multiplication, then obviously we can look at it and we know it's scalar multiplication because we're multiplying a scalar by a real number by a vector, right? So we just know by looking at the context of the problem. Okay? Oh, let's see here. Okay, so now, let's look at a question. So let's look at something here. So a question that will come up, that we'll answer now, is why specify in the definition. So we've gotten these 10 things, these definitions of a vector space, right? So why specify the condition that 1 times vector v is equal to vector v? Why specify that condition, but not the condition that 0 times vector v equals the 0 vector? Because that's not one of the conditions. So one answer is, well, that's just the definition, right? That's the definition, and you got to follow the rules to go on. And you know what? That's a valid answer, right? But a more satisfying answer is going to be with how we use the definition in our study of sample vector spaces, okay? Because people who work in this area, who do a lot of research in this area of vector spaces, wanted to make sure that they work to develop the right balance of power and generality, right? So this definition is shaped so that it contains the conditions needed to prove all of the interesting things and properties of spaces and linear combinations. And as we proceed, we shall see this in action, okay? And also we're going to add, you know, we'll talk about more things as we build on too, but for right now, we're just dealing with those 10 conditions. This will come up later, okay? And as we proceed, we shall derive all of the properties natural to the collection of linear combinations from the conditions given in the definition. So anyway, we'll leave it at that, and we'll move forward.